Good morning, everyone. We have today a great scientist, one of the leaders in South Africa. It's an honor for us, and Ange, I am really thankful to you that you accepted our invitation. It's a real honor to have you, especially today that we are celebrating through many activities the role of women in science, and you are an exceptional example of what women are capable to do in science. I am really inspired by what you are doing in South Africa. So Ange has done a lot of things. She is mainly working in the field of structural light, but she has been doing other research related to this. For example, she has done high power laser applications, and she has done structural light, of course, generation, characterization. She has published over 30 papers in some of the most important journals like Nature Photonics, Nature Communications, Physical Regulators, Optics and Photonics Advances, and so on and so forth. She is now the chair of the conference, Laser Beam Shaping Conference, organized by the SPIE, which is part of the Optics and Photonics. And today she will, she's now working at the University of Witwatersrand. She worked for 10 years in the laser center, in a laser center in South Africa, and she's a lecturer at the University of the Witwatersrand. I think you started in 2018, right? Not so long ago. Anyway, it's a pleasure for us to have you here, Ange. I will let you talk now. I just want to remind all the students and everybody else that you can type your questions directly on the chat, or you can actually, if you like, you can ask your question directly. We will open the mics for you. While Ange is speaking, I will please ask you to turn off all your mics and cameras so that we don't interrupt her. And Ange, welcome, and thank you very much for accepting our invitation. So please go ahead.
Yeah, sure. Thank you very much for the invitation and for the very kind words. I think you may have oversold me. And I actually, when you asked me which day, I happened to just pick today, but I didn't know at the time that it's actually women in STEM careers. So hopefully that's quite fortuitous that it just happened to be today. But thank you very much for the invitation and for the very kind words. Yeah. So hi everyone, my name is Angela Dudley, as Carmelo said, and I'm from the Structured Light Lab at the University of the Witwatersrand, which is located in Johannesburg in South Africa. So the talk that I will be giving today pertains to digitally controlling both the phase and the polarization structure in optical fields. I'm first going to introduce and discuss a fair amount of concepts and techniques that we use, and then I'll present our approach for developing optical fields whose polarization structures not only rotate about their optical axis, but we can actually make them to accelerate independently from their spatial profile. And then I'll just briefly cover on how we actually extract these polarization structures by doing digital Stokes polarimetry. So before I go into the content of the talk, I just wanted to highlight where our group is based. So sure you all know, so we're in South Africa, and as the name describes, it's just the country that's located at the bottom, the southern tip of Africa. And our main cities are Pretoria, so this is where our union buildings are based, and it's seen as the executive branch of our government. And for us as South Africans, it's very well known for what we call the jacaranda trees. So if you can see here, these purple trees. And it's always known amongst the students that if you see the jacaranda trees coming out in full bloom, so when you see the purple flowers coming out, and you haven't started studying for exams, then you know you've left it too late, because these flowers always arrive at the same time as exams. So if you see those flowers, then you know you've left studying a little too late. And then we have Johannesburg, which is where our university is based, and this is the largest city in South Africa. And then I'm sure a lot of people know Cape Town. So this is where our Houses of Parliament are based, and it's also home to Table Mountain, which is a prominent landmark for tourists. So then if we go into Johannesburg and we go to our university, so this is the University of the Witwatersrand, and it's colloquially termed WITS, so this WITS over here. And it's located in Joburg, and it's actually the oldest university in South Africa. And it's often placed in the highest ranked universities in Africa. So we're usually neck and neck with UCT, which is the university in Cape Town. So between ourselves and UCT, we're the highest ranked universities in Africa. So these photos here, these two photos here, are just of our Great Hall, where our graduations take place, and a lot of ceremonial lectures, and sometimes they even have concerts in the Great Hall. And then if we move to the physics department, which is where our group is based, this is just located on the left-hand side of the Great Hall. So if you have to walk along here, just behind these trees is the physics building, and that's where our research group is based. So coming now to our research group and what we do, the core focus of our group is on structured light. So this refers to the shaping of light in all of its degrees of freedom. So such as the time domain, the frequency domain, amplitude phase, and the polarization structure. So what you see here in the background of this slide is just the shaping of light in its amplitude, so in its intensity profile, which we achieve through doing shaping the phase, which will become more evident when I get further into the slides. So these are just examples of CCD images of intensity profiles that we've shaped in the lab. Our group, in terms of developing structured light, looking at ways as how you can create it and how you can measure it, there are three main areas in which we apply and exploit the structured light. So the first is just in classical optics, and the main motivation for us generating structured light just with classical optics is to enhance the bandwidth in optical communication systems. And then there's a part of our group that also investigates tailoring the structure of light internally to a laser cavity. So what we call in terms of performing intracavity beam shaping. Just for the remainder of this talk, I'll only consider extra cavity beam shaping. So that's shaping the laser beam external to the laser cavity. So you're not doing any shaping inside the laser cavity. So not since it's all external to the source. And then finally, there are also students and researchers in the group that also exploit and probe the structured light for high-dimensional quantum entanglement systems. So for achieving things such as secure quantum communication and doing quantum imaging as well. So those are just the three core areas that our group applies structured light to. So as I mentioned earlier, near the start of the talk, I mentioned that structured light just refers to the shaping of light in all of its degrees of freedom. So in the time domain and the frequency domain. So if you wanted to create things such as ultra-short pulses, or in the spatial degrees of freedom. And this is the core focus of our group. So such as doing shaping in the amplitude or intensity profile, the phase profile, as well as the polarization profile. So the creation of structured light is dependent on a variety of optical components. So these range from things such as just apertures, which would do your amplitude shaping, geometrical phase optics, diffractive optics, more for changing the phase of your light, looking at Spatialite modulators, which I'll cover in a whole lot more detail in this talk. And then also other optics such as digital micromirror devices, I'll briefly touch on those. You also get metamaterials that do beam shaping, as well as just general polarization optics. So in the case of controlling both the phase and the polarization structure of an optical field, one can create these very topical, spatially structured vector beams. And I'll go into more detail as to what those are a little further into the slide. So this is combining both the phase structure and the polarization structure to create what we call vector beams. So one of the first questions that people usually have at this point is, well, how do you create this spatially structured light? What is it that you do in order to get your spatially structured beam. So if we consider this case over here where we just have our Gaussian beam, so something like a laser pointer, what is it that you need to physically do to be able to get some unique spatial structure? And in order to do that, I'll show you in terms of how we do that in our lab. So how we physically do this is actually just based on a long-standing and well-known technique of holography. So I'm pretty sure everyone with an optics background knows about holography. So this illustration over here just illustrates the concept of holography. So you have some object that you wish to reconstruct. You illuminate it with a reference beam, and this reference beam is reflected over here after illuminating the object beam. And then by interfering it with a portion of the reference beam, the interference pattern that you obtain over here is what we call the hologram. And then by just running this whole process in reverse and illuminating the hologram or the interference pattern with your reference beam, you can then reconstruct the object. So this theory has been around for many, many years, and everyone who's done an optics course will know this. But it's only recently been possible to implement holograms digitally with the use of liquid crystal displays. So a device that makes use of these liquid crystal displays is, for example, just a Spatialite modulator. And this is just an example of one of the types that we use in our lab. The fundamental working principle of these devices, and I'll cover this in more detail in the next slide, is just based on electrically controlled birefringence. So allowing the phase of the incident beam to then be modified by just addressing each of these pixels by a unique shade of gray or a unique phase profile. Although these devices are very small, and I've tried to illustrate this here, this is the actual dimension of the liquid crystal display for the Spatialite modulator. They offer very similar resolution and refresh rates to high definition displays. And this allows us to actually control and shape our light both dynamically and in real time. The types of SLMs, the Spatialite modulators that we use, the liquid crystal display, so this component over here, which you can see just in this photo over here, that's connected to this flex cable, is the essential part of the device, and it consists of 1920 pixels by 1080 pixels, and each of these has roughly a dimension of 8 micrometers. So as I mentioned in the previous slide, the mechanism of the display is based on electrically controlled birefringence. So here each pixel is just addressed by 2 electrodes. So for example here, if we just take 1 pixel, it's addressed by 2 electrodes, and the molecules making up the pixel are aligned parallel to these electrodes, which when then applied an electric field, just forces the molecules to tilt in the direction of the applied field. So the incident light that you then use to illuminate the Spatialite modulator over here then needs to be linearly polarized and parallel to the axis of the liquid crystal molecules, so that when the molecules tilt in the direction of the applied electric field, the refractive index that's seen by the light then changes accordingly, and since you get a change in the refractive index, you consequently get a change in the phase of the light. So in the case where you have no voltage applied across the pixels, so in the case here where you're addressing no phase variation, so if your hologram has just this black color, there would be no phase modulation that would occur in your incident beam. But then as you start to increase the phase variation in your interference pattern or your hologram, so you're varying the shade of gray in your interference pattern or hologram, you actually then are just changing the phase modulation in your incident beam by getting these molecules to just tilt further and further. So we've already seen that these devices, these Spatialite modulator devices, are capable of modifying the spatial structure of optical fields. So this is just a video here, and this is all done in real time, just illustrating that these devices can actually shape the beam in real time, and you can get really numerous spatial profiles that you want. And then we also use these devices to just mimic free space propagation in our lab. So usually if you want to investigate how a beam propagates, we need to physically actually move a camera along the propagation axis of our beam, and this can often make alignment in the lab very problematic. But by making use of this digital approach, this allows us to simulate just the behavior of beam propagation while using static optics. So everything remains static, but you are digitally encoding the beam to actually propagate. And then we can also assign these holograms to have specific carrier frequencies, which allows the beam to be controlled and shifted to various spatial locations. And this process of doing this by assigning the beam to various spatial locations is just what we call multiplexing. And we've also shown that these devices are wavelength independent, meaning that we can vary the spatial profile of multiple beams of different wavelengths simultaneously. So here in this experiment, we just used a supercontinuum source to illustrate this. Then another device that is capable of modifying the spatial structure of light that we make use of is just a digital micromirror device. So the development of these devices, these digital micromirror devices, has stemmed from very well-known data projector technology, which just consists of these very small moving mirrors, which are used to project light to specific locations. And this then modifies the amplitude of the incident beam. So these devices offer advantages in that they're much cheaper than your Spatialite modulators. And since they're based just on moving mirrors and not liquid crystal technology, they can also be used with beams with much higher power. So in the order of moving from milliwatts now with your Spatialite modulators to the watt range. So we're extending some of our work looking at moving towards high power laser beams, shaping laser beams with higher powers. Now that we've covered some of the introduction into modifying the spatial profile of light, I would like to look at some interesting aspects such as creating light that has an angular accelerating intensity profile. So our work into creating angular accelerating light actually stem from our interest in optical fields that carry what we call orbital angular momentum, such as these vortex and Laguerre Gaussian modes. So these azimuthally varying beams contain a phase singularity, which you can see in the intensity profile over here, around which just the phase or the wavefront of the light varies and increases azimuthally. And the rotation of this wavefront can either be defined in either a clockwise direction or an direction. And if we were to view only a vortex mode, so such as this mode over here, you would agree that it would make it difficult to be able to monitor the angular acceleration. But if we looked at something such as a superposition of vortex modes, which produces this petal-like structure over here, this would allow us to then track the rotation of a single petal. So we'd be able to actually look at how one of these single petals actually rotates as the field's propagating. And then by just removing diffraction effects, this will also allow us to measure only the angular rotation without any contributing factors. In order to achieve these two requirements, so you want to have a petal structure so that you can see the petal actually rotating as the field propagates and not have any diffraction effects, we make use of the superposition of higher order Bessel beams, which are also carriers of orbital angular momentum. So an approach to generate Bessel beams was first published by Durnan, and he discovered that if you had an annular ring structure placed in the back focal plane of a lens, and you illuminated it with a plane wave, you can then reconstruct your zero order Bessel beam. So then by just repeating Durnan's experiment, and instead of illuminating this ring slit structure with a plane wave, illuminating it with something with an azimuthally varying phase profile, you can then generate your higher order Bessel beams. And then by subdividing this ring slit structure into multiple ring slits, so here we've just got two ring slits, and encoding each of those with its own phase variation, you can then obtain these superpositions of higher order Bessel beams. So for example here, we just encoded an azimuthal phase profile of +3 and -3, and you get this superposition that consists of these 6 petals. And all of the fields that are generated in this process just propagate over an extended distance in which they do not diffract. So these fields are what we call non-diffracting fields. So within this diamond region over here, this field will not diffract. So one of the aspects that first piqued our interest in these superimposed fields is that even though these fields can be engineered to possess no overall orbital angular momentum, so for example here, if you take an azimuthal phase variation of +3 and superimpose it with one that's -3, you'd agree that overall the field should carry no orbital angular momentum. We actually still witnessed a rotation in the resulting optical field as the beam propagates. And this is actually due to the slightly differing wave vectors that make up this optical field. So that's assigned by these ring slit dimensions. So we were also able to quantify the rotation rates and show that it's dependent on two factors. So the difference between the wave vectors, this delta k over here, and the azimuthal order of the azimuthal phase profile that's encoded in the ring slit. And so in this case, you can see that this angular rotation is constant. So now we want to ask the question is, well, how can we make this actually accelerate and deaccelerate as the field propagates? These two videos just illustrate here where we have a clockwise rotation for our 6 petals and then an anti-clockwise. So the reason for this is that for this constant acceleration is that the phase contained within each of the superimposed Bessel beams varies linearly. So you can see here in this phase profile going from a phase of 0 to 2 pi, this phase just varies in a linear constant manner. So there's a constant rotation as you're going around this phase, azimuthal phase variation. So then it then follows that in order to be able to obtain an angular acceleration of the beam profile, one needs a nonlinear variation in the phase profile as a function of the azimuthal angle. And this is just illustrated in the following phase profile. So if I just jump back, you can see here we have a very linear phase variation, but now we have something that is nonlinear, this nonlinear phase variation. And that's just illustrated on the plot on the. So for this work, in order to be able to demonstrate this in the lab, in terms of developing fields that have this angular acceleration, we still use our Spatialite modulator, and we addressed it with 2 ring slits, where each of the ring slits then has a nonlinear azimuthal phase variation. And we then view the Fourier transform of the field. So if this is our ring slit over here on the Spatialite modulator, we're just repeating Durnan's experiment by looking at the Fourier transform of that ring slit on the CCD. And these intensity profiles are then just recorded on our CCD. And if we look at the results for that, so you can see that when we have the linear phase variation, you get your constant rotation. And this is just also illustrated in the isosurface plot over here. But as you start to encode a nonlinear phase variation, you get this field that has sections where it's accelerating and deaccelerating. And that's illustrated over here in the isosurface plot, where you look at these sections of very tight rotation over here. And the following plot just on the right over here just depicts the measured angular position during propagation for varying degrees of nonlinearity. So over here, we just had for theta, which is our morphology parameter. If you set that to 0, that you just get the constant rotation case. And as you increase and vary that morphology parameter, you can get your nonlinearity to increase, and you can get the acceleration to vary. So this is just to illustrate that we can actually control the angular acceleration of the intensity profiles of these optical fields. So up until now, we've only considered the phase of the light and not so much its polarization structure. But when we combine these two things together, when we're looking at both the phase and the polarization, this is what we term vector modes or vector vortex modes. In order to just visualize what vector beams are, I'm going to make use of just the Jones formalism. So if we consider scalar polarization, The following Jones matrices over here just illustrate the horizontally polarized field and the vertically polarized field. So if we have a field whose horizontal and vertical components are just represented by the exact same mode, so this is just illustrated over here, we can construct our linear, so our horizontal and our vertical polarization, and our having superpositions of those, we can then just obtain our diagonal and anti-diagonal polarization states. And then by just introducing phase shift, we can then get our right and left circularly polarized light. But then if we consider the case where the two components are represented by different modes, so different spatial modes, so here the horizontal component is these two lobes orientated horizontally, and the vertical component is two lobes orientated vertically. We can construct what we call vector polarization. So for these particular cases, either the radial polarization or the azimuthal polarization. And with these beams, you can see that the local polarization state is linearly polarized at different orientations across the beam. So either at azimuthal orientations or at radial orientations. So now if we just consider scalar polarization, so this is just to kind of illustrate the concept further. The following vortex mode, which consists of right circularly polarized light. So over here I just have an illustration of a vortex mode that consists of right circularly polarized light. And if we were to view that through a rotating polarizer, so you had a polarizer in your setup and you were just filtering out specific polarization states depending on the angle at which you orientated the polarizer, you can see that the spatial profile of the beam does not vary. And actually this is just a video over here. I think it's already stopped, but this video here is just a video of the intensity profile of the optical field as you're rotating the polarizer. You see that for scalar fields, that as you rotate the polarizer and select out various polarization states, the spatial structure does not change. But if we look at something like a vector mode, so it has the exact same spatial structure, the exact same intensity profile, but if you were to pass it through a polarizer and select out various polarization states, so here we're selecting out just the vertical form of diagonal, then anti-diagonal, and moving closer towards the vertical state, now back to the vertical state, you can see that the spatial profile actually varies. So it's inhomogeneous as you're rotating the polarizer. And this was just illustrated as well in the little video over here. So this is always a good test to know if you have a vortex beam, is just to pass the beam through a polarizer, rotate the polarizer, and if you can see the spatial profile of the beam changing, then you know you have a vector beam. So why are we interested in these spatially structured vector beams, and why have they become extremely topical, is that they can be used to offer increased bandwidth for optical communication. So now you have two degrees of freedom. You have both the spatial degree of freedom and the polarization degree of freedom in which you can encode information, as well as similarly in terms of having these two extra degrees of freedom, you can look at doing high dimensional quantum entanglement. And also the possibility of having interaction-free detection with quantum imaging. And these modes are also known to produce much tighter focal spots when they are focused with a high numerical aperture. So recently in our work, we've been interested in generating optical fields whose polarization structures can be made to not only rotate about their optical axis, but can also be controlled to accelerate. So similar to the previous case that we saw with the intensity profile actually accelerating, we now try to apply that and do it with the polarization structures and get them to accelerate independent from their spatial profile. So before we could create angular accelerating polarization structures, we first needed to figure out how to create rotating polarization structures, or to have these rotating polarization fringes or polarization petals. So if we assign optically varying azimuthal phases, so for example over here, to orthogonal components of electric field, so here these orthogonal components are just denoted by the x vector and the y vector, we can then show that we can obtain these polarization fringes and get those to actually rotate by then just having the superposition of oppositely handed phase variation between them. So this is just mathematically illustrated over here in the following form of the electric field. So we have this orthogonal superposition of our two polarization states, where this θ1 and θ2, this phi1 and phi2 just represent the phases associated with each of the orthogonal polarization states. And each of these phase variations is just denoted here by this opposite-handed phase profile. And now if we combine our previous case of creating angular accelerating spatial intensity profiles with the generation of our polarization fringes, which we saw in the previous slide, by just encoding orthogonal components of the optical field with superpositions of two Bessel beams with opposite azimuthal indices. So here we have our superposition of two Bessel beams, and we have our two opposite-handed phase profiles associated with each. So this is just the construct that we used with the intensity profile actually accelerating. And we can then get azimuthally accelerating polarization structures. And here, this theta over here just denotes that morphology parameter, which gives rise to this nonlinear phase variation. So each of these orthogonal fields is just a weighted superposition of a Bessel beam where you have two oppositely handed azimuthal phase variations. And when we set this morphology parameter to 0, this just reduces down to our constant rotation case. While if we set that to something that's non-zero, so for example here, just pi/3, we can get the accelerating rotation is then achieved in these azimuthal, in these polarization fringes. So the two videos over here, I think they might have stopped playing. Let me just see if I go back and forward again, if they'll play again. Just illustrates the constant rotation for the polarization structures and then just the accelerated rotation. Over here you can see that in the bottom case over here we get that polarization structure actually at certain points it starts to speed up and then slow down. And here just the red and the blue just denotes two orthogonal polarization states. So the blue is just your left-handed and the red is just your right-handed. So in terms of performing this in the lab in an optical setup, what we have is we've got our two scalar petal beams, which we just generated on our Spatialite modulator by encoding our ring slit hologram. And then each of those petal beams was then directed to a 50-50 beam splitter to then combine those. And since both petals initially have the same polarization state, so in the case of our experiment, they were both horizontally polarized. One of those beams is then passed through a half-wave plate to just rotate its polarization state from horizontal to vertical. So this is illustrated over here, what the two beams at each point in the path of the interferometer would be. The two beams that then enter the 50-50 beam splitter would just have the following mathematical form, where one of these would be in the vertical state and the other one in the horizontal state. And then by producing this vector beam, we can then, after this beam splitter over here, we can get this angular accelerating polarization structure by just controlling this morphology parameter denoted by this theta. This illustrates over here capturing the Stokes polarimetry data to be able to look at what the polarization state is across our optical field. And I'll show a video in the next slide of what that actually looks like. So the slide over here just illustrates this angular accelerating and deaccelerating trajectory of the polarization vectors as the field propagates, just illustrating the right circularly and component of the resulting vector, which is just denoted here by this red isosurface plot, and here as well in this illustration just by the red vectors, and then the left circularly polarized state is just denoted by the blue. And we can see that as the right component begins to accelerate, so where there's this very tight twisting, we can see that the left component actually starts to de-accelerate. This can also be visualized by just following the trajectory of the Stokes vector along the Poincare sphere. So here, if you just focus in on the green arrow, as this is just the case where we considered the superposition of the horizontal and the vertical case, the other arrows where we looked at different superpositions coming into the beam splitter and the resulting field, we can see that at certain regions along the field, along the sphere, you actually get this arrow will either slow down or it will speed up. So it's just illustrating that the Stokes vector is actually either accelerating or deaccelerating. So this is the final part of the talk where I just want to give a brief overview as to how we measure these polarization states by Stokes polarimetry. So a popular approach to extract the state of polarization of an optical field is to make measurements of what we call the Stokes parameters, which is just referred to as Stokes polarimetry. So it's already very well known. It's been well known for many, many years, and I'm pretty sure everyone here already knows it, that these Stokes parameters can just be obtained by measuring 4 intensity profiles. So visually, this just involves measuring the right circularly polarized state of light, the left circularly polarized state of light, to extract both your S0 and your S3 Stokes parameters. And then by looking at 2 other polarization states, so looking at your diagonal and your horizontal, to then get your remaining Stokes parameters, your S1 and S2. So the standard conventional approach that most undergrads would probably use in their lab using just static polarization optics is usually by having a quarter wave plate and a linear polarizer, setting the quarter wave plate to 90 degrees and the linear polarizer to a diagonal state to get your right circularly polarized light. And then just by rotating the linear polarizer to the anti-diagonal state to get the left circularly polarized state. And then to get the remaining 2 intensity profiles, you would just remove the quarter wave plate and rotate the linear polarizer to 45 degrees to get your diagonal, and to 0 degrees to get your horizontal. And then once you have these 4 intensity profiles, you can then calculate your Stokes parameters. But for us, we looked at forming a digital analogy to this conventional approach. And you can see that from the conventional approach, there are 2 aspects that we require. So there's a need to be able to independently control the orthogonal polarization states. So to be able to introduce a 90-degree phase shift. So that's what the quarter wave plate's doing. And then we also need to be able to measure in an orthogonal polarization basis. So either you could measure in your horizontal, your vertical, your diagonal and anti-diagonal, or your right circularly polarized and your left circularly polarized. So the first requirement that we need can just be achieved by using a polarization and sensitive beam shaping device, which is just our digital micromirror device over here. And by just encoding a 90-degree phase shift, we can get this to perform the action of the quarter wave plate. And then the second requirement where we want to project into 2 orthogonal polarization states. So here we decided to choose the right and left circularly polarized states. We use an optic which is known as a polarization grating, and this just acts like a beam splitter for right and left circularly polarized light, a lot like a polarizing beam splitter. And by combining these together, we can then, and introducing this 90-degree phase shift on our digital micromirror, we can then extract all of the 4 required intensity profiles, so your right, left, diagonal, and horizontal, to be able to perform Stokes polarimetry, which then allows us to reconstruct the state of polarization of our optical field. So here are just some examples of us using that technique to extract the state of polarization for just a scalar beam. So here we just had a right circularly polarized optical vortex, and you can see that the state of polarization across the field is very uniform. And then for a vector mode, where you can see the state of polarization is actually varying azimuthally around the optical field. And we can also use this approach to extract the intermodal phase between the orthogonal states of polarization. So here we were just comparing the conventional technique of just using the static optics as opposed to the digital technique. And you can see there's a little bit of spherical aberration in this case, just because we had to propagate the beam further. So you pick up this spherical aberration in the setup that we had to develop for this approach. And by just introducing our digital propagation technique, so by simulating the propagation of the optical field on our Spatialite modulator, we can actually combine these two techniques and look at the intermodal phase between two orthogonal states of polarization. And in this case, we looked at and were tracking optical vortices. So we could look at how the phase of an optical vortex actually varies as the field propagates. This actually brings me to the end of the talk. So before closing, I just wanted to end with a photo of our group. This is a very outdated photo, so it's actually pre-COVID days. But we're hoping to take a more updated photo once it's kind of safe for all of us to have a photo together. So we often have, so it's mainly consists of a lot of students, so masters and PhD students. We have a couple of visitors that will come now and then and visit. Yeah, so we're always looking for new people to join the group. I know it's a very difficult time at the moment in terms of travel, but we really love having visitors visit the group. So anyone who wants to keep that in mind, just send me an email. And so on that note, I'm going to end with my email address and say thank you very much for your attention, and I am happy to answer any questions. So I don't know if I should.
Thank you so much. Please just leave your email address there for some time. Yeah, so that they have time to write down. Thanks so much. While we wait for some questions, yeah, okay, we already have some questions. I will read them to you, and then I will ask also some myself. So there is a comment by one of our researchers. Thank you for such an interesting talk. Have you tried different topological, this is the question, have you tried different topological charge in your phase elements to produce the accelerated vortex beams?
Yeah, so, okay, I was actually looking to unmute myself, but you guys can hear me. So we have looked at that. So if I go back possibly to that slide. So actually looking at the different, like increasing the topological charge of the field, you can actually get the field to rotate slower. So you can actually vary the rotation of the field by changing the topological charge of the superimposed when you're making those petal structures. So if you vary the topological charge of what's involved in your superposition, you can get the field to actually rotate at different rates.
Yeah, so one way to change the acceleration is just by changing the topological charge.
Yeah, it's like tuning.
Phase, right?
Yeah, you can use the topological charge almost like as a dial, like to be able to tune it to control the acceleration and the deacceleration.
Yeah. Okay. Great. So there's another question. It's first a comment. What an impressive work! I am about to get my PhD. I work on time domain terahertz spectroscopy, but my interest in structural light has grown over the years. Do you think that is possible to look for a postdoc position in this area?
So definitely, I mean, we're always keen within our group. So definitely with our group, and there's a lot of groups around the world that are looking at like in different areas. So I know of a group in Finland who are looking more at using structured light just for studying quantum aspects. So using it in quantum entanglement, doing some quantum imaging, some secure communication. And then there's also, I mean, we haven't really looked at this too much within our group, but there are groups that also look at using the structured light and optical tweezers. So having a sample trapping, let's say like silica beads or your biological tissue, and actually encoding the beam with some structure to be able to transfer these interesting properties to the beam, to the beads, to the particles. So if you have a beam that carries orbital angular momentum, you can actually get your little particle to actually rotate if you trap it with a beam that has orbital angular momentum. So there are a lot of groups that would use structured light in a lot of their applications. Yeah.
Yeah. Okay. Yeah.
I don't have like a specific link to maybe suggest, like recommend like a consortium of people that are doing structured light, but definitely a postdoc in structured light, I'm very sure you'll easily find a group.
Yeah, great.
And even our group is very keen. We're always keen for new people.
Yeah, exactly. I know that. Great. So I guess he can email you later. I mean, you can email Ange, and
yes,
you can probably ask her directly. There's another question. What type of polarization grating are you using in Stokes polarimetry?
So the polarization gratings, I actually have to think a little bit about it because we got it kind of custom made from a collaborator. And I think it might still be based on some form of liquid crystal display, like sort of liquid crystal technology where the liquid crystal molecules are aligned in a certain way that to make up that grating. So it was just a very long time ago that we got it, but I think it is based on some kind of liquid crystal polymer that they've used to make that device. I don't know if that that probably doesn't fully answer the question.
Yeah, but anyway, it's custom made, right?
Yeah, so it's a custom made optic. So it's actually by a group in at North Carolina State University. And I'm trying to think of the guy that heads up the group. It's his name's like on the tip of my tongue. It was like such a long time that we visited them. It's like maybe 8 years ago. Yeah, but they do like, I think what they call like OLEG technology. I can't fully remember what the acronym stands for, but if you search for North Carolina State University and maybe look for something like OLEG technology, you'll probably easily find their group.
Okay, yeah.
And make these devices.
Great. So he's asking if by any chance, do you know if it's an isopolymer film?
Yeah, sorry, that I probably wouldn't know.
Yeah, okay, great. Thanks, Ange. I'd like to ask you something. If you go back, please, to your slide where you show the polarization structures rotating, I have the impression that it's not only rotating, but it's also changing. Yeah, that one. Yeah, that one.
Yeah.
Yeah, it's changing between like linear and circular polarization, maybe?
Yeah, so it's very interesting. So when we were doing this and like looking at the simulation, I guess like in the mathematics, you could kind of see like this angular variation, but in terms of what the physical mechanism is, that at some point your beam is predominantly right, let's say it's predominantly left circularly polarized over here, yes, and then right circularly polarized. Like what is introducing this angular variation? Like here it stays constant, but over here this angular variation is either getting bigger or smaller.
Yes, exactly.
I don't have an answer actually for what the physical mechanism is that's doing that.
Okay, great, thanks.
But it's just it's an interesting thing to note. Yeah.
Yeah, okay. There's another question, which is actually what I was going to ask you. It's by, I think it's by one of our students. She's asking, well, she's thanking you for such an interesting talk. And she is asking, I don't know if I miss it, but are you looking to work with this topic in a particular application?
So in terms of the angular accelerating light, not really. It was kind of just a fun side that we did. So we have applications for using the vector beams, this kind of like marriage between phase and polarization. But to try get accelerating polarization structures was actually just a kind of a fun question to see if we could answer. So it was sort of just, well, we've done it with the phase profiles, but could you actually do it with the intensity profiles? So I mean the polarization profiles. But we don't actually have an application in mind for it. Yeah. So if anyone has a cool application, that would be great. But I guess when we started it, we didn't have a particular application.
Yeah, I guess it's just a very new topic. I mean,
yes, yeah, it was kind of like a nice to see if you could actually physically do it. Yeah.
Exactly. Yeah. I mean, as I told you, when I read this paper, I was shocked because we thought we were doing exactly the same, but it turns out it's not the same. So these are just new topics and applications. We are still looking for applications, I guess, right?
Yes, yeah. And I mean, it's actually, I'm very relieved that it wasn't the same as,
Yeah, exactly.
what's going on.
Anyway,
But yeah.
yeah. There are no more questions, Ange. Thank you so much for accepting our invitation, for giving us this very nice talk, and we look forward to have you in the future again, giving us another talk, and um, we will send you shortly just a small present to thank you for giving this talk.
But Shane, that's
Uh,
really, really sweet. Thank you for the invitation. I think this is such a great initiative for institutes to do at the moment.
yeah, exactly. We have no other option. Plus,
Yeah.
if we're doing it like this, we can get great talks like yours. Otherwise, we wouldn't be able to have you here.
Yes, yeah, yeah.
Exactly. Thanks so much, Ange, and thank you everybody for attending this talk. Um,
Oh no, sure,
that's it.
sure. Thank you.
Yeah.
Thanks.
Thanks, Ange.
Thank you
Bye
very
bye,
much. Thank
everyone.
you.